It's recording. Okay, let's do a bit of recap. What did we do? Can I please have, let's go with Jaden. Last session, 8B. Tell me something you remember. Venn diagrams, very good. We learnt Venn diagrams. How many regions? One of these. Did we run out? Must be this one. How many regions are there in a Venn diagram that you must know because it links to cardinal maps or two-way tables? How many regions does a Venn diagram have? Can I please have, who was here last session? Let's go Jada. There are 4 regions. Very good. So we have 4 regions. I'm just going to quickly draw a Venn diagram. And then I'm going to highlight them. So this is A, this is B. Okay, AB. What is this region called? Can I please have Samuel? So the one I'm coloring in blue, which is not done very well, just this section here. What would that section be called?
A, not B.
A.
Intersection,
not B. Very good. And there are 4 of them. So if I just try to color them, or maybe do this. So that's the middle. That's second. You got another one in blue. And then finally, I'll leave it as white as the outer region. Now let's convert that to a two-way table or cardinal maps. A dash, or B, not B. And you got your total here. The 4 regions all represent, that's the intersection between A and B. This is what is not A. And, oh, sorry, I did it wrong. The colors over here. Not A, but this is A, not B. And this is the not A, but B region. This is A intersection B region. And the white region is your 4th region. Okay, so there are 4 regions, 4 notations that you need to familiarize. Not A, intersection B. A intersection B, and then finally the last one is not A intersect, not B. Okay, so these are some basic year 7 and 8 notations that we need to get familiar with. But then last session, Sanvi gave us a rule, okay, and we called it the addition rule. I gave you a perspective about it. There were 2 ways of getting there. You can look at it through the cardinal maps, or you can look at it through the diagram, but regardless, both ways will get you the addition rule. Now, out of curiosity, hands up if you remember, what was the addition rule equal to again? So A union B means that you group A and you group B together, so all of this region, the blue, the purple, and that lined section. What was it equal to?
Probability A plus probability B minus probability A intersection B.
Beautiful. This is the rule for what we call the addition rule. And what it basically means is, and I know Joanne said probability before, it works for probability or it also works for just counting numbers. Okay? Now if I draw it again, so here's my A, here's my B. All right? When we say A, I'm essentially saying I want this group. So you color all of A, that's all of A. Then I say color all of B, so I want all of B. So whoever's in A, I'm going to include, and I say union means let's group them together. I'm going to group B. Now see what happens when I color B, and I do, actually I should do yellow. Maybe I should do green and yellow will work better actually. Let's do it again. So color A, then I color B. Now when I color B, so this section here is green. But as soon as I venture where they overlap, usually they do they change colors usually, but in this case they didn't change colors. So usually that changes to mix between green and yellow and it turns blue. Was it blue and yellow? Blue and yellow makes green, is it? Oh, it does work. It's my complementary colors that I was wrong. There we go. So the idea is when you color B, see there's a problem. B, when I color B, the reason why this changes color is because I'm overlapping. That means I've doubled up the center. That's why part of the rule, they say, this is my colored B region, this is my colored A region, but as soon as where they mix, it changes color because it's overlap. I'm doubling up on it. That is why you needed to subtract the double up. Okay? Now, if that visually didn't make sense to you, then I've got an example that we can do together. So today's lesson is essentially linking from last session. Your Venn diagram, corner maps, you still need to know this. This is the problem-solving section. And then you're just delving into the idea of problems that involve addition rules specifically. Okay, so 8C and 8B are very tightly tied together. The only difference between two is one's focusing more on A union B. The other one's just playing around with either of these tools. Okay? Before we get into the problem, what's the tip that I gave to you last session? When is it best to use a Carnot map? What did I say? Because I usually tell my U12s this. Nishi? Calculations. And what do I mean by that? In Year 12, you get problems something like this. So they might say probability of A dash is equal to 0.7. Then they might say probability of B given, actually you guys haven't learned conditional probability yet, so I'll take that away. Let's say probability of B is 0.4. Then they will say something like find probability of A dash intersection B. Something like that. So the idea is that if you try to put this information into a Venn diagram, you can. It's just a bit harder to visualize the little details. But if you use a Carnot map, it actually gives you more information that allows you to then solve the problem. I probably didn't give you enough information there, but that's the gist. That's when you know it's a calculation. When is it a Venn diagram? It's when you want to see a bigger picture. You just want to put it all summary into one thing. You just want to see what it looks like. So when I'm explaining theoretically, that's why I use a picture. Because had I done this way, that would have been harder for you to understand the rule, but it's much easier to see when I do a picture. Okay, so this gives you a better overall picture. So when you're zooming out just to see what the problem is actually dealing with, this one's for calculations, which most times in Year 12, it's a calculation problem. So most of my Year 12s are doing this in the exam. Okay, less so that. There was a problem that I remembered that only one from 15 years that I saw that you would use a diagram to help you, but most times it's that one. Okay? All right, let's do this problem together. Here you go. So say we have, cross that off, wasn't 15, it's meant to be 23. In the class, there are 23 people in the class. We survey if they prefer apples, so A for apples, and capital B. Remember the capital letters is for sets. So sets means groups or collections. So capital A for apples, number of people who want or prefer apples, number of people who prefer bananas. Out of 23 people, we know that 6 people like bananas only. Keyword only. In the Venn diagram, where should the 6 go? So if you were going with a picture, so let's say you used the Venn diagram as your tool, where would the 6 go? Yes, Mira. What was that? Over here?
Yeah.
Right there? Very good. Okay, so this is where it's B only and not part of A. Okay, if they said, and I'll just color the region just to make it clear, that's B only. If they didn't have the word only, so if the only wasn't there, then you would have colored all of that. Then you would have said banana. Number of people that like bananas is 6 in total. But because they said bananas only, then I must only include this region here. So it means that in your Carnot maps, the 6 does not go, total of B is not 6. It's actually B, not apples. So the 6 goes here. Okay, so that's just a small distinction between where you would put the numbers if you're using two-way tables versus a Venn diagram. Okay? All right, next one. Where does then the 4, actually most people will know this one, 4 people like both bananas and apples. That must go where? Can I please have Samuel? Where would 4 people like both apples and bananas go? A and B. Very good. So here's A and here's B. So you would have 4 here, or where the region where both A and B overlap. That'll be 4. So just looking at the diagram here, we can see visually it makes sense that 4 and 6 actually gives you the picture or all of B. Whereas if you did a cardinal maps approach, it may not have been obvious. 4 plus 6, even though you can write it out as 10, sometimes students may not realize this actually represents all of B. Okay, so that's why I said that this is good for visualizing the problem. This is good for calculations. So in the diagram, it's not obvious that it's 10 right there, but here it's very obvious that total of B is 10. Yeah? All right, and the last one, 9 people like apples only. So 9 people like apples only. And again, the key word is apples only. So Jaden, where does 9 go? Very good. Left side in the A region only. So here we go. A only, not to B. So together that should give you 13. And then from here, now you can work out the outer region from this region. You can go 9 plus 4 plus 6, which gives you 19. How many more do I need to make a total of 23 people? 4. You can do it that way. Or in this one, what's nice about this is it actually gives you all the numbers in the same way, but this one just gives you more details just from looking at the numbers perspective. Okay, so in total we knew it was 23, so that had to be 10. That means this had to be 13, but if that's 13, this must be 4. In some ways, it's a bit easier to get all the different regions. Okay, so this is up to you depending on which ones you're going to build your skill on. Most of my Year 12s, I'm still trying to get them to approach it this way. Most times students approach this way when they see this information because I think you've been trained to just think in Venn diagram mode. I do prefer that you start working in this region because most of the time the questions are calculations. Okay, let's do a problem together. Oh, actually, let's fill out the formula again. This is the one that Joanne was saying. So when we're talking about probability, it's different to number. Okay, number of items versus the probability. So this is the notation for number of items. So remember, that's the cardinal number, which represents number of elements in group A. Out of curiosity again, do you remember what elements mean? Hands up. What's elements mean? Una. Items. Very good. So how many items in group A? Another word for group. From exercise 8A, what's another word for group? Set. Very good. So that's our proper notation or terminology, elements, set. So technically when we say cardinal number, it's the number of elements in set A. Okay, so if I do n bracket A, that's what it means. So here, Joanne said before, A union B, we already know it's group all of A, so probability of A, total, plus total probability of B, minus probability of A intersection B. So probability is different because you need to know the total and the number of favorable outcomes out of the total. Versus cardinal number, you don't need to know. It doesn't have to be a proportion, doesn't have to be out of the total, it's just a number. Okay. Reason why I'm emphasizing the two, my Year 12s just recently did a SAC. Yes, it was just before the holidays. And one of the questions got them to fill out a Venn diagram. And we showed them the symbol, which meant universal set. And we wrote 1,000. Means that what's in this diagram should be numbers, not probability. So we had a few students who started writing. They got the right probability for each region. But the problem was that's in probability. We can't give a mark for that. So they lose marks based on that idea. Okay, so it's just being careful with the notation. One's probability, one's number. Okay, yep.
Could you draw like the universal sign a little bit?
Oh, yeah, sorry. Universal sign is like, I kind of look like that. That's how I do it. Okay, but if you look in your textbooks, usually they don't, sometimes they even do it like this. Just like that. But I see in the textbook, it's like that. So I do a little loop on the top, and I kind of do like a 3, like a backwards 3. Okay, so I just do that. Most people understand that means the epsilon symbol. Epsilon symbol. Salon Sybil? All right, let's do this problem together. Example 1, 2 events, A and B, are such that. So this is a typical problem where it's in a year 12 section. If they give you numbers like this, you should be thinking of cardinal maps and two-way tables. Here we go. Probability of A is 0.5. Probability of B is 0.6. And probability of A union B is 0.75. Thank you. Without this table, you can solve it. It just feels a bit harder, but with the table, it allows you to solve it a bit easier, or at least you feel like you're working towards something. So let's pull out the table. We've got two events, A and B, or two sets, group A and group B. And we know that they're saying probability of getting A is 0.5. So this table now, it won't represent numbers, it will represent probability. But if it's going to represent probability, what's the total probability? What's the maximum probability you can get? 1, because 100% is 1. So that means this must be 1. They told us that all of A, the chances of getting all of A, so this represents all of A, then the chances is 0.5. 0.5 goes here, because that tells me the total for A. That means that the chances of not getting A must be the opposite of that. If there's 50% chance of getting A, then there's 50% chance of not getting A. Then they told us that probability of B is 0.6. So you got 60% chance of getting B. That means how much of a chance do you have of not getting B, Toby? 0.4. Beautiful. Okay, and then lastly, now we still don't have enough information to fill out the table because you need a third piece of information. Yeah, they gave you A union B, so that makes it a bit trickier, right? But same idea. We know that the union is actually these three regions. So if you're confused why I just said that, I said these three regions make up A union B. Why? Just think about the Venn diagram again. A, B. This is the region for green, A intersection B. So here's my green. A only is in blue. And then B only is in yellow. Can you see once I color all those three regions, that gives you A union B. All of A, all of B. So another way of looking for A union B is these three numbers must add up to 0.75. That's another way of looking at it. Okay? Or we also know the rule is probability of A plus probability of B minus probability of A intersect B. Okay. Here we go. We can also use this rule to calculate that. So you can also say, well, we know that the total is meant to be 0.75. We know that all of A is 0.5. And we also know all of B is 0.6. So we can now actually work out A intersection B by doing algebra. Let's work it all together. 0.5 plus 0.6 gives you 1.1, but you need 0.75. So what do you minus? Yes, so you can do it algebraically, or you can do it logically from here. But let's just because the numbers might look a bit confusing for some of you, I'm going to just write it as 75 equals 50 plus 60 minus x. Okay, that might be easier for you to visualize it. So 50 plus 60, you told me 1.1, which is really like 110. So 110 minus x equals 75. And from here, you can solve for it by either adding x on both sides and then minus 75 on both sides. So it becomes x equals 110 minus 75. Yes, all I did there was minus 75 on the left, minus 75 on the right, plus x on the right, and then plus x on the left. So negative x plus x cancels out, 75 minus 75 cancels out, and then you're left with 110 minus 75. And you've got x on this side. So what does this link to? X is equal to 35. Very good. So 35 in terms of decimals or percentage should be Good. So this now tells me probability of A intersect B is equal to 0.35. Whoops. Now if you know that's 0.35, it's much easier to then fill out the table. So this must be then 0.35. Then you can work out 35, add what, it gives you 60. That gives you 0.25, very good. And that means this is 0.25 as well. And then finally, the last one then must be 0.15. There you go. Now that we've filled out the table, it is much easier to answer the question. Probability, oh, why is it asking for A union B? That should have been A intersection B, sorry. That should have been intersection B. That's what we're meant to find. But I guess it works out. We found intersection B anyway. Last one. What would the B answer for B be? What's probability of not A intersection B equal to? Very good. 0.25. Okay, that's the yellow region. Not A intersects B. You see what I mean by the table being very useful for calculations? You can do it Venn diagrams, but you can see it would have been harder to visualize and picture. This is best for calculations, and these are generally hints to use Econo maps. Okay, so get used to using Econo maps for those points. All right, let's flip over. I'm going to give you 5 minutes. See if you can do example 2. Now, for those who don't play cards and you aren't familiar with this, because I've taught it many years and I realize that not all students know about deck of cards. Deck of cards have 52 playing cards in total. There are 4 suits. So you got clubs, diamonds, hearts, spades. So there's 4 rows or categories. Yeah. Then in terms of the number system, we've got 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King, and then Ace, we can treat it as 1. So it's kind of like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King. Right? So there's 13 cards there. 13 numbered cards by 4 different suits. 13 times 4 is how you get 52. Okay, and that's why I put a picture here, because some students don't know deck of cards. Yeah? There we go. Have a go with this problem. Example 2, I'm going to pause the video for 5 minutes, and then we'll go through the answers together. And it is now recording again. Okay, let's check our answers for the first half anyway. Most of you should get the first half. Can I get a show of hands for the first half? You got all of them correct. So 6 out of 6. It should be 13, 4, 1. So at least this side. So 3 out of 3 so far. And then 6 out of 6, meaning you've simplified your fractions. 1/4, 3/4, and 1 out of 52. Keep your hands up. All right, that's good. That's a good percentage. Very good. Next one, which following on from what we just learnt, union, which is A union B, you just then use what you've got so far to then solve. So most of you should have got this one. So A union B. And you said you got A, 13 out of 52. I just changed 4 out of 52. And you should get 4 out of 13. Hands up if you got 4 out of 13. Okay, yeah, that's a good percentage again. Good. Okay, now the last one. This one, I've seen 2 answers that have been the same. So just be careful. The word or. When you say or, think about the language. We're saying, what's the chance of choosing a jack? Okay, so there's 4 jacks. Listening. Thank you. Choosing 4 jacks or. So it means I've got now another pool of options I can choose from. So this said jack. So I've got 4 options here. Or, so now how many options are there that is not diamond? Okay, so I said jack or not diamond. Now diamonds, that's 1 suit. In 1 suit, there's 4 suits in total. So there's clubs, diamonds, spades, and hearts. So diamonds take up 1/4 of it. So if I don't want diamonds, there are 3/4 of 52 that's left over. So you should be adding 3/4 of 52 plus the 4 jacks. Does that make sense? That's the sort of counting way of doing it. This is how I did it. I did it using the union formula again. Jack, union, not diamond. Chance of getting jack is 4 out of 52. Diamond, I already knew is not diamond is 3 out of 4 suits. And then what's the chances of getting a jack and not a diamond? Well, there's 4 jacks, and out of those 4 jacks, 3 out of 4 is not a diamond. So, if I added them together, J plus not D minus the intersection, these two cancel, you should end up with 4 out of 52 and 113. But now I'm thinking about it, does that even make sense? Is it 1 out of 13? I've done something wrong. Let me think.
How could be minus 3? So it could be 3 with 4. You still get jack with 3 out of 4.
Ah, this is the issue. Thank you. I made a mistake. Thank you. I just realized in terms of the picture, there's so many cards. How can it be 1 out of 13? All right, so let's fix that then. So 3/4 of 52 times 13 times 13. That's 3 times 13, 39. What's that work out to be? Oh, you were right. No, I was wrong. 40 out of 52 reduces down to 20 out of 26. No, divided by 4, 10 out of... Is that better? Hands up, you got 10 out of 13 and not did what I did. All right, beautiful. Thank you, team. Let's stop the video there.